Hey, this is Professor Alejandro Enriquez. Welcome to Chapter 5. Chapter 5 covers lipids, which are the name for fats and oils. We're going to be going over lipid structure and function, chemical function, structure and functions in the body, how they're digested, absorbed, and also how they apply to our knowledge about how they apply to our diet. So let's start off with this chemical structure of lipids. Lipids are a lot of different molecules found in the category of lipids. The thing that makes them all in common is that they're almost entirely or entirely made with carbon and hydrogen only. The diagrams you can see here on the right are actually organic chemistry diagrams where they replace they don't rack out every letter C and H. They just put each vertex is a little carbon atom. So as you can see, there's basically hardly any. There's a few oxygens, a phosphate, but it's almost entirely just carbon and hydrogen. And because carbon and hydrogen have about the same electronegativity, that means that they are ultimately they are hydrophobic molecules. That's the thing that separates them from carbohydrates, especially. So there's a lot of different kinds. We can see that there's this group called the sterol group, or sterol rings, that are notably cholesterol is a good example of. Cholesterol is this guy with all of the rings forming the sort of shape, unique shape. Cholesterol is not metabolized for energy, but it is a lipid, and so it's processed along with other lipids when we eat it, and it has a lot of important functions in our body. The second molecule you can see was labeled a free fatty acid, is basically a long chain of carbons bonded to each other with hydrogens occupying all the empty spaces around it. The end of it has a carboxylic acid, which is why it's called a fatty acid. And that carboxylic acid is used to attach the fatty acid to other things. So, for example, a glycerol molecule will accept 3 fatty acids to form what's called a triglyceride. Which is the third molecule here. And you can see the triglyceride has 3 long tails, and then what it is, they're all attached to what's called glycerol, which is the small molecule that holds them all together. Triglycerides are the normal kind of fat that we have, that we store energy in our bodies. We store fat as triglycerides. It's also what forms our fat tissue. Another really important lipid molecule is actually what's called the phospholipid, which is similar to a triglyceride, but it only has 2 tails. The third spot on the glycerol is attached to phosphate, which is a polar molecule, which is why the phospholipid is partially polar and partially nonpolar, and that's what causes it to form the lipid bilayer that goes around the outside of the cell, forms the cell membrane. So these are all different versions of lipids. They're all lipids together. They're all processed kind of in the same way. They're all absorbed the same way, as we're going to see in a little bit. One really important thing about fatty acids, they can be saturated or they can be unsaturated. So basically anywhere on these long tails, each of these long tails is the fatty acid. Anywhere where you see look like a little equal sign, you see that's what's called an unsaturation, where there's a hydrogen missing. And it's got a double bond there. And so because it's missing a hydrogen, we say it's not saturated with hydrogen. It doesn't have all the hydrogen it could hold. So that's why you know that if there's no double bonds like that, you'll know it's saturated, and all the ones that have the double bonds are what's called unsaturated. There's also another kind of fatty acid, which is not normal. This is not natural. It's not formed by plants or animals. It's created in laboratories or in industrial processes. It's called a trans fat. And a trans fat is where you have a double bond, but rather than having the double bond in this kind of kink, forms that kink, makes that change in the shape of the tail. A trans fat actually kind of it looks very similar to it looks very similar to a saturated fat, but it has a double bond in it, and so that makes it that it can't be processed because we don't have enzymes that can break down trans fats, and so those are only formed by processes like hydrogenation. So when we ever look on packaged food and it says hydrogenated vegetable oil or whatever, that normally has trans fat in it. So you're gonna want to stay away from those because trans fats can't be processed normally by our body, and they kind of just take up space and don't contribute and can lead to health problems. So this is the chemical structure of the lipids. They have a lot of different functions. The most famous function that fat has in our body is for storing energy, and the reason for that is because lipids store a lot of energy. Have a higher energy density, we can say, 9 calories per gram of fat, which is as opposed to proteins and carbs, which is, you may remember, is 4 calories per gram. So that's more than twice as much energy per gram, which means that lipids are a great way to store energy. Just what you want to have fat so you can store energy. That's the most important function, the one we're all aware of. We all know if you eat too much food that you don't need, you store the excess as fat. We know that everyone kind of grows up intuitively knowing this relationship. But there's a lot of other functions that fat has in the body. First of all, that storing of energy is really important. You don't want to underplay that, because if you don't have enough fat reserves, you have trouble providing enough energy to your cells through gluconeogenesis to make it to your next meal. So that's one major issue with fat. A lot of other things that lipids are really important for include forming our cell membranes. As I mentioned, phospholipids are used to create the phospholipid bilayer, which makes a cell membrane around the cell. Fat tissue also is important for protecting vital organs. For example, your kidneys are padded in fat, which is very important because your kidneys are very sensitive organs with a lot of little tubes. And if those tubes rupture, you can have all kinds of kidney problems. Insulation is another key thing, having a fair amount of fat. So, for example, if you look at mammals that live in the ocean, like whales and dolphins and seals and so forth, they have a large, thick layer of fat to help keep them warm because it insulates. It's a poor conductor of heat, which is good. You want that, especially if you happen to live in colder regions of the world. Lipids are really important also because all lipids mix together, just like water mixes with water-soluble things, all fat-soluble things mix together. So when you eat fat-soluble vitamins like vitamin A and vitamin D and so forth, absorbing them is commensurate with absorbing other lipids. So and they're actually moved through our body through the same transport proteins that we're going to see in a little bit that our regular other cholesterol and triglycerides are moved with. Cholesterol as a lipid is really important for a lot of things, including creating bile salts, which in turn helps us digest other lipids, and also vitamin D, which is a lipid-soluble vitamin, but it actually can be produced, unlike most vitamins, it can be produced in the body, but we actually need sunlight to do it, right? So it's actually sun will strike 7-dehydrocholesterol and convert it into cholecalciferol. Now, we can also get cholecalciferol in our diet, but if you look, vitamin D2 and D3, it's hard to get enough. There's not a lot of cholecalciferol in most of the foods we eat, even the ones that are supposedly rich in vitamin D. And so sunlight is usually how we make up the difference, but you can only do that if you have cholesterol in your blood, in your diet. And then last thing that's really important about lipids is that they add satiety to our foods. Protein and lipid both add a lot more satiety, meaning that if you eat, like 8 ounces of fatty foods, you're going to be full longer than if you eat 8 ounces of starchy food. So because carbohydrates break down very quickly, and you'll digest it more quickly, and you'll be hungry again sooner. And so that having that fat in the food helps it sit in your stomach longer. And it's not technically listed as an important function, but another thing is alcohol actually mixes with fat also, ethanol. And so they say if you want to try and slow the absorption of alcohol into your stomach, you're supposed to eat fatty foods first, because the fat will mix with the alcohol and it will sit in your stomach for longer and it won't go into your blood as quickly. So just a fun tip for you there. All right, so we need to digest foods like lipids before they can be absorbed. The way that before we can actually chemically digest lipids like triglycerides, we actually have to break them apart, because the enzymes that break apart triglycerides are water-based enzymes, like basically all of our enzymes are. And so they're actually lipases are actually used to break down triglycerides. But before the lipases can mix with the triglycerides have to be split apart, and they're split apart from each other from these big blobs with bile. Bile is secreted from the liver. The liver actually uses chemical materials to produce bile. The bile is then stored in the gallbladder, so if you have any problems with your gallbladder, like any gallstones or anything, you have problems digesting lipids, that's the usual result. You can actually have your Gallbladder is one of the few organs you can actually have removed surgically, and you're just going to be completely fine, basically. When they remove your gallbladder, normally they take the duct coming out of the liver and attach it directly into the duct going into the small intestine. So basically, you're constantly secreting a small stream of bile into your small intestine rather than storing it and releasing it all at once. So people who have their gallbladder removed usually have to avoid eating too much fatty food at one time because they may not have enough bile in their intestine at one time to break apart all of the fat. The thing about bile, it works by splitting hydrophilic and hydrophobic, or allowing hydrophilic and hydrophobic things to mix because it has a hydrophilic and a hydrophobic region on it. So it's kind of like a phospholipid, but it's a chemical which its shape allows it to penetrate and mix into fatty blobs of fatty materials. It basically works the same as soap. And when I ask in class, usually, what's the function of soap? Everyone says, oh, it's to clean. But that means that if you get oil on your hands and you put soap on your hands aren't clean. You actually need to run water, and then the oil will come off with the soap in the water. If you just have oily hands, you run water over it won't take it off. So that signifies that the true function of soap is to allow oil and water to mix. In the same way, bile allows oil and water to mix so that the oils, the fats in your food are broken apart, can then be broken apart further by pancreatic lipases, and then most of them form what's called micelles, which are little absorption molecules, little balls of fatty materials, so balls of little glycerol, not the glycerol molecules, excuse me, but the fatty acids, cholesterol, etc. They go into what's called the lacteal, which is in the small intestine. There are a lot of little lacteals. And the lacteals, which are part of the lymphatic circulation, carry these lipids through into your bloodstream, and eventually that blood gets to your liver. The liver will take these chylomicrons, which is the name for little balls of fat that enter into your blood, and reconvert them into lipoproteins. Lipoproteins are really important because lipoproteins are used to move particles of fat from your liver to your fatty tissues, and also from your fatty tissues back to your liver. If you ever go to the doctor and you get a blood test and you actually look and see, they actually say, the doctor may look at it and say, oh, your cholesterol's kind of high, or oh, your cholesterol's really good. Usually they don't actually mean your literal cholesterol. What they're actually talking about are the lipoproteins, because there's two kinds of lipoproteins that move fat through your body. There's low-density lipoproteins that move fat from your liver to your fatty tissues, and then there's what's called high-density lipoproteins that move fat from your fatty tissues, like your adipose tissue, back to your liver to be broken down and turned into sugar, which is, again, gluconeogenesis. So the doctor's actually looking at the ratio. You want to make sure that basically you have the right ratio of LDLs and HDLs. If you eat a lot of fatty food and you don't exercise, you don't use it, you just store all the fat, you'll have a higher ratio of LDLs, of low-density lipoproteins, because more of the fat's being put into your body. And this can be potentially hazardous because some people may have a predisposition to move those fatty tissues onto your major arteries as well. They may get stuck on your aorta, for example, which and your other major arteries, and clog them up, which can lead to heart attacks, premature heart attacks. So fortunately, usually the answer in this case is just to exercise, because exercise increases your high-density lipoprotein levels. Because when you exercise and actually go on a run, and it's not really weightlifting as much, it usually means cardiovascular exercise. That means that high-density lipoproteins are produced in the liver. They go and collect fat from your fatty tissues, your adipose tissue, and also your arteries, if there's any stuff caked on there, and move it back to your liver for gluconeogenesis. So that's why you'll see the doctor looking at your HDL and LDL levels and talk to you about your cholesterol and say maybe you need to exercise more or anything like that. Of course, we have to have this adipose tissue, so it's very helpful to have fat in our diet. But there's different kinds of fat in our diet, and fats have a very negative reputation because of that high caloric density. So because there's so many calories in fat, if you're counting your calories, you tend to start cutting fatty foods from your diet, which is good because you don't want to, if you want to count your calories and not have too many calories, you do want to not eat excess calories you're not using. But there's a bit of an issue where there's different kinds of lipids. The unsaturated fats are usually a lot healthier for you. They're actually usually very healthy. And the saturated fats are the ones that increase your blood cholesterol levels and so forth. They tend to be more problematic. I'll mention that normally what you see is unsaturated fats are what's found in plant oils. So that would obviously be like corn oil, olive oil, etc. And they're usually liquid at room temperature. If you look at saturated fats, because they don't have those kinks in the tails, they pack together more nice and tight. They actually are normally solid at room temperature. So that's butter, bacon grease, etc. Because if you notice, if you take a hot pan and put bacon on it, the bacon is all solid, but then the fat melts off the bacon. That shows you that that was saturated fats. Most animals usually produce saturated fats, and then plants produce unsaturated fats. Although you do see some exceptions. For example, the polyunsaturated fatty acids, like omega-3 and omega-6 fatty acids, they'll have multiple double bonds. Those are found in some cold water fish and so forth. So in general, you're trying to restrict your calories, it's a good thing, but you still want to make sure you have a good proportion of unsaturated fats in your diet. People who tend to cut out unsaturated fats completely tend to create new problems in their diet. And also make sure if you're trying to count calories to just look at the nutritional information of everything you eat. It can be very tiring to do this at first, especially if it's confusing. It's like, what am I even looking at? But usually saturated fat is listed on there. And there's a lot of things with hidden fats. A lot of baking, a lot of the book actually mentions pastries. There's some pastries that have a high concentration of fat, but you wouldn't know it. It just seems like any other bread product. But as it has a high concentration of fats, it's going to add a lot of extra calories that you may not need, unless you're hoping that it adds satiety. Although anything with a lot of starch usually has a lower satiety anyway. So if you're trying to restrict your diet, you should be staying away from bread products. You're going to want something with more starch and more unsaturated fats in it. Because usually baking, they're going to use butter, which is a saturated fat. And of course, above all, make sure you're watching carefully your trans fat. Try and minimize that. Be careful. If something is fried, it probably has at least a little trans fat in it. Even if it says 0 grams trans fat, normally the FDA allows you to round down if you're under 0.5 grams per serving. And sometimes you actually see these saturated, these very unhealthy processed packaged foods actually make their serving size so small so they can round down to get. So you'll see like a package of like Oreos, and it's like one serving size 2 Oreo cookies. That way you can keep their serving size so low that there's less than half a gram of trans fat, so they can round it down to 0. So just watch your serving sizes and keep an eye on how much fried food you're eating, because frying the food does, especially processed food also, is going to have a lot of, or anything that has hydrogenated vegetable oil in it. That's what's going to have a lot of trans fat. Okay, so hopefully that makes sense. That's just a brief overview of Chapter 5. Hope that all makes sense and registers. And make sure you participate in the discussion boards. And we'll see you again next week.